Okay. So yeah, today, sorry I didn't have this up earlier, but yeah, we're going to be doing this one. I'm going to move this up to the top. So this is the lecture. All right, so I'm also going to be doing some demos as we go through it. So we're going to talk about network analysis in GIS today. And the first thing that we're going to do is talk about what a network is. All right, so a network in GIS is implemented as a set of connected lines. And those lines can actually represent lots of different flow entities or phenomenon. Okay, we typically think of them, and lots of the examples today will be roads, but there are all sorts of different networks that we can develop. We could do rivers, telecommunication lines, and we could even do like ocean current connections, things like that. Networks in a GIS, they can be directed and undirected. We'll talk a little bit about what that means. Okay. Most networks most of the examples that I draw from, like the road network, is it always the same to travel in one direction versus another direction? No, it's different. There's, sometimes the speed limit's usually the same in both directions, although I'm sure there are some cases where it's not in the world. But even if we throw speed limit out, there are other things that affect the direction of travel. If we were traveling on an ocean current, we'd experience that in even bigger detail. So we have to deal with ocean currents going one direction. We have to use more energy or fuel to travel in that direction than against the grain. The same with an airplane, I suppose. And networks could also be planar versus non-planar, and we'll talk about that here in a second. But a network can be modeled in a GIS, and we usually bring things up in a GIS using a top-down approach. But there are cases where there are roads that cross over each other where it's impossible to turn onto the other road, right? I'm talking about like on a freeway overpass or something like that.
We've got here in Hattiesburg going down the interstate, several bridges that cut across it. You can't get on, you have to go way around to get across it.
Exactly. So when we model our network, there are cases where we would want to model something like that. And really, networks, I'll make the argument right now, but we'll show this in a little while, but it's almost as if a network, it's based on a mathematical concept that's not really spatial at all. Really the only thing spatial about networks in GIS is we've drawn a representation of a connection that may represent a real world entity, but that space has only a little bit to do with how well that connection is made. So we'll look at that in a second. But there are two different types of networks that you can model inside of GIS systems, and they're modeled slightly different. One is a transportation network. It's called, ArcGIS calls it a transportation network. But this is your network that's concerned with, I guess I'll just say things, because it doesn't necessarily need to be people. It could be other entities traveling from one point to another in space. Okay. So that's the transportation network. Along predefined routes. And then a utility network is more concerned with the connections of entities and how they distribute a quantity. Okay, how that quantity can be distributed. So utility network example would be something like an electricity network, or you might say, okay, if I make breaks here and here, am I cutting off people from this network, or water network? We're not going to talk about that one too much. Okay? We're going to talk a little bit more about the generic flow network or transportation network. All right, so in a GIS system, when we go to build a network, it's a series of connected lines, and those connected lines can be accompanied by junction, what we call nodes, junctions or nodes. These aren't required to build your network, but they do allow you to attach attributes to the relationships. Okay, so you need to have the places where they flow. Those are called the edges or the links, the flow lines. You need to have those, and then optionally you can have junctions or nodes in your network. Okay, so you can have points or lines in your network. Okay, so travel on the network is usually decided by an agent. So this is in real life. In real life, what happens is that this is what we're trying to model. We're trying to model this concept of travel along a connected network once it's been established. So in real life, when you decide to go somewhere, you're the agent, the person deciding to travel from one place to another. And the way that we're going to model this network that can look like this, is that each of these edges or links are going to be assigned an attribute. So these are vector GIS data layers. Those edges might represent roads, and we could give them an impedance, a cost of traveling through every edge, and also at every junction we could specify a cost to travel through a junction. So a junction could model, well, let's get some examples. What could a junction model? A point. If we were talking about roads. A four-way intersection. It could model a four-way intersection, and we could assign a cost to travel through that four-way intersection. Actually, let's back up for a second. What could be some impedance or cost values that we might apply to either a junction or an edge?
How busy it is.
Traffic light time.
Congestion of traffic.
Yeah. Right.
Slow down time.
So time.
Yeah.
Time is a very often used impedance or cost value assigned to a network. And we've all familiar now. When I first started teaching this 15 years ago, we didn't have Google Maps that we could get on, and we're familiar with the fact that Google Maps, it has those little red lines and green lines and yellow lines. You've all used that before, right? So it's obviously changing these impedance values, changing the costs at different time periods. But that's what's really happening inside of a Google's data set, is that every line, every connection in there is assigned a value on how long it takes to traverse that line, both in a to direction and a from direction. So if we looked at the attribute table, we would see a to and a from attribute, and they're being updated in real time, right? So what we're going to do today, or what we're going to demonstrate today, is not updated in real time, but those attributes would be updated in real time. So these are line features with attributes. These are point features with attributes, and the attributes represent travel time, or they can actually represent some real cost, like how much money it would take to travel in a certain way. Go ahead.
Yes, those round nodes, they could be periods of time during a particular day because it might cost them more, as they were saying, because of traffic, but those based on time zone. At 12 o'clock midnight, it might be the cheapest because you don't burn any fuel, there's nothing to construct you. But 8 to 3, each one of those might be modeled based on the cost value of it going through those particular areas.
Right. So yeah, the time is important, okay, and you're right about that. But what I'm saying is, with each of these features in our network data set have a attribute that says that has an impedance or a cost associated with it, okay, and that may change over time. It may constantly be changing, but in today's examples, we're just gonna have one value for that. But you could, I'm just trying to tell you, you could see how, if that value is changing, then the answer as to where we're going might change. Okay. So time and distance are often used as costs, but we could actually use like money. Like if we're trying to determine, like let's say we had a public transportation network. We're trying to determine how to get from point A to point B. Well, we could have one column that had the cost of traversing every point and line in time, one column that had the cost of traversing every point and line in distance, and one that was how much it costs in terms of actual money, like you had to pay the bus fare, pay this fare, whatever you had to pay. And then we could provide the end user with all three of those choices. Okay. All right, so that's what the cost is. Now you could also have, you could build a complex network, and a few years ago Google started doing this, right? So we've used. I'm going to go to Google Maps since I've been referencing it. Maps.google.com. So now I have the ability to go to, I don't know, so if I wanted to go do directions,
Google Maps gives you directions. Oh, you use directions.
I'm trying to get the directions part. I think you can just click on it and say directions from here, right? Directions, there you go. My starting point is, all right. So here, if I was gonna travel from Laguna Beach up to LAX, I could do that. And so there's a network data set that's actually driving what you see here. And this is the shortest path that was chosen. But I can all of those possible lines to travel have attributes that tell how long it takes to drive a car, but they also have attributes that say how long might it be if I was just to use public transportation. Well, first of all, there's some nodes and edges that are totally removed from that data set because there's no public transportation. So now this is the quickest public transportation method. It's going to take 3 hours and 34 minutes doing public transportation. And if I just wanted to walk, might be a pretty walk. How long would it take me? Now there's less restrictions. Now almost everything's based on distance, and you can see the effect of that in the network. being a much more direct route. But it would take me almost a day to walk.
Shows up elevation there, right?
Yeah, it even shows up elevation. I didn't know that it did
I
that.
didn't know that either.
That's so cool.
Yeah.
So,
And biking. I used to bike all over Orange County when I was a kid. Biked 50 miles one time up. I lived in Irvine. I cycled way up here, and then I came down this little river down. Anyway, so it'd take roughly 5 hours. This is the trip my wife's taking right now. She's coming back. She's been gone about a week and a half. That's where she's staying, and then this is where she's flying out of. So anyway, those are the different choices, and these are all just driven by attributes in the network data set. So the network data set has those attributes, and it might have a different attribute for the mode. Well, it does have a different attribute for the mode of transportation, and at a particular junction, if you're on a bike, it might say, well, there's no cost. You just kind of sail through a particular junction. But if you're on in a car, you have to stop, or vice versa. And so you can model a very complex network with just this very basic idea of a set of edges and nodes, where the edges and nodes have attributes that constitute their impedance. So it might have to have, if it only has one set of attributes, then there's only that one moment in time, and there's only that one type of transportation. But if it has attributes for all the different things going either direction, and we got 4 different types of transportation, and then we start talking about time, having it updated all automatically. But still, what's actually driving it are the nodes and edges and the impedance value. That's the crux of it. Yeah.
So Google Map, it was showing you the method of locomotion, but it also had a combination, as you were saying, if it's bicycle, car, truck. But it also has there are a few more values in there, like could be a breakdown in the road, because it's updated continuously. So if there's a slowdown, your time's going to change too, and they're changing it too. That's probably one of the attributes you're talking about, maybe the accident, stuff like that. Are those permanent?
Well, if an accident occurs, what's happening to the underlying data is that if a road becomes impassable, its impedance value just goes to infinity, or is a very, very large number. Okay, and so then you can't get past that road anymore, and so you can ask the network again to find the least cost path.
Right.
Yep. Yeah. So if we have our GIS data loaded on our computer, our local computer, it's not updated in real time. But Google's data is being updated in real time. So they have sensors, and those sensors are actually your phones, and for the most part, and those are all getting sent to Google, and Google is evaluating how fast people are moving on various roads all the time, and they have computers that are reading that information in, and then what's happening is that they've got computer programs that are going into the attribute table and editing what the impedance value is on those particular roads at that time. Does that make sense?
So that's when you're not using Google Maps too? Your phone's like a data sensor?
Oh, yeah.
Like if you're just driving with your phone, you're a data sensor?
Yes. Yep.
Okay.
That's how they get all this information. Like this information. That's how they know that it's going slow, is because,
Phones are going
that freeway's packed right now, so there's hundreds of people that all have Android phones in their pockets going, and they're being sent up to Google, and Google's using that information to determine what the traffic is on that road.
User location.
Also, what's really cool now is the user uploaded data.
What's
like
that?
speed traps that said what's
Oh,
the
yeah,
signal
yeah.
that
I went up
is
to the
speed traps now too.
I went up to the BYU Tennessee football game a few weeks ago because I went to BYU as an undergraduate, and I was driving home because I just went for the weekend, and yeah, it went off. It was a new thing for Google, but they've adopted it from Waze. So it went off, and I slowed down, and there was a policeman right there. It was pretty
Tells you when
wild.
there's cops around?
Yeah, it tells you when the cops are around now.
I need that.
I don't.
I thought that was something like people had to go in and be like, hey, there's a cop sitting here.
Yeah, so I don't know how they get
Like cop location.
Waze you used to put it in.
Yeah, you put it in and then like it had to take so many confirmations before it like show
Right.
up and stuff.
So I don't know because there's no place to put it in Google, but still they're
Maybe
reporting
just
it.
measuring when people like stumble the bridge.
That could be.
Or it could be like the police radio scanner or something. They're picking up on that.
There's someone listening to the scanner they're inputting your stuff.
Dr. Ray,
Yeah.
when they send the information to those nodes and they know what kind of safe distance you get within that particular node, they're gonna send you the updated data for that particular space and time where you're at. They'll know where you're at. So they're not looking at your phone, they just send it to them. They send the information to that particular area. You get within how many feet of there, they'll probably let you know, bam, it's somebody just reported it. So it's constantly, like you're saying, it's constantly updating timely bits of information, but it's very helpful for whoever is on there, whoever they look for.
Yeah. I'm pretty confident that they're just reading our phones.
Yeah.
That we're not. It doesn't take any active thing on our part, and I wouldn't even. I mean, that's just my opinion, but just because you turn location services off.
It happens with your,
Google actually runs the hardware and the software. The software. So who knows what's actually going on there? But we know they tell us that it's not being shared with anybody else, but it doesn't mean they're not collecting it.
right.
Anyway.
That's like with your laptop. You can do this at home. This is the real thing. If you pull up, I have a laptop that has a mic on it, and you pull up Google and just let it sit there, okay? And then pull up a couple web pages that have like regular ads on it, okay? Now sit there and talk about something like dog toys for like 15 minutes, and then reload those pages and see if those ads don't change to dog toys.
Yeah.
I swear that has happened to me.
Yeah.
I swear.
Anyway, so
That's a real thing.
I didn't mean to get off into conspiracy theories. Back to network. The point here is that these lines can be assigned multiple different costs. So it's not just a single cost, and that the Google example was meant to show that how that could actually be implemented. So a utility network, by contrast, is basically just flow happens across it. It's almost always directed, meaning that every entity has a particular way that it travels through the network. It's usually based on utilities or circuits or something like that. That's the one we're not going to focus on too much today, or really other than that. Yeah.
So if a network is a directed network, that's pretty much like one ways, like it only goes one way. Is that what directed versus undirected means?
Yeah.
Okay.
And it said the path can be changed by the agent, and that'll be us, right? It can't.
Right. So on a utility network, we're feeding stuff through it, whether it's water or electricity, and so it's not deciding where to go on its own. Even though in transportation network we're assuming that the agent will either we'll show a few different applications here, but we're going to assume in some cases that the agent will always take the best path. In other cases, we're assuming that the agent wants to know what the best path is. Right.
So is it like a immutable network where you can't change it? It's almost like a little programmer that you told in Python by immutable, in the sense that you can't do any kind of thing to change what it's doing once you enter that particular area. You just gotta go with what's on the program.
Well, the reason that we're not spending a bunch of time on the utility networks is because they're a little more boring. They're just like, is it connected? Yes, it's connected. Kind of type questions. Whereas a network like this, transportation network that's modeling the flow of an agent, we can ask it all sorts of kind of interesting questions like, what's the closest thing to me? And we'll show some applications. But I don't know that there's a real connection between whether it could be changed or not. Both of these can be changed, right? And they're both modeled in similar ways in that they all contain edges and junctions, okay? But one is more about either predicting where things are going to go or being able to ask, how do I get there? I mean, it's actually more similar to what we talked about last week with capability suitability analysis. So we can either use it to model where people might go or entities. The agent does not have to be a human. Like, we could use this to model where migratory birds might flow if we know that they prefer different things. We can set the networks that they would fly, the fly paths. We can give them different weights and kind of just show where they would go. Or I didn't plan to show this, but maybe I will. I published a paper back in 2011 where we modeled the connections using ocean currents. We modeled the connections of coral reef larvae, like where they would settle given ocean currents, and so we basically said which coral reefs are connected to which other coral reefs, and how connected are they using a network. So in ArcGIS, so now we're getting into ESRI lingo here. In ESRI lingo, a utility data set is modeled using what they call a geometric data set. So we're not going to cover how to create that or how to even use it in this class, but this would be like, let's say you could get a job and you work for a utility company, then you'd need to know this. And basically, you just build all of your connections, and it contains the tool that gets developed contains tools for helping you to verify that connections are being made and that they're appropriate connections. So you can set up all sorts of rules. You could say that two pipes can't connect together without a fitting, okay? Or two wires can't be connected without a junction box. And so you model all the nodes as different things like junction boxes and fittings, and you model all the edges as things like wires or pipes, and you could make all sorts of rules. Show me all the places where 6-inch pipes are fitted to 2-inch pipes because we need to fix those. We need to make the 2-inch pipes bigger, and in those cases, things like that.
Is there a tool for making that kind of data set, or a set of tools for making that kind of data set, or is there just a process you think to make that kind of utility data set?
Yeah, there's a tool for it, but it's not the one that's called Network Analyst, which is the one for doing transportation networks. So, there is a tool. I actually don't know if it's been implemented in ArcGIS Pro or not. The reason why I say that is because actually, even what we're talking about today, the tool doesn't exist yet in ArcGIS Pro to build either of these types of networks. At least I'm pretty sure about the utility network. I'm positive about the transportation network. So right now, you can't build your own transportation network in ArcGIS Pro. You have to open up our catalog and build your transportation network in our catalog, which is the older version of the software. Okay, but eventually they'll put that data in here. What you can do is if you have network data set A that has all of the same structure as a new network data set B that you want to create. In other words, if network data set A is already built and working, and it has the same attributes, in other words, it has the same costs and they're named the same thing, And then you have another data set over here where you have all the lines and the points ready to be modeled as edges and nodes in your new data set. You could say, okay, copy the way this network data set's set up and apply it to this data. So you can do that right now in ArcGIS Pro, but you can't like build it all from scratch. In other words, you can't say to build it from scratch. It means, okay, this is the edges data set I want to use. And you can actually have more than one edges data set. This is the edges data set I want to use. These are the costs associated. These are the cost fields associated with that network data set. So right now, you can't do that in ArcGIS Pro. That's only in our catalog. But the answer to your question is I don't know if that's in ArcGIS Pro yet. I can look that up after class probably. Okay, so in ArcGIS, the transportation network is modeled using a network data. That's what's called a network data set. So that's what we're going to talk about today. And a network data set can be analyzed in what's called network analyst. So the tool network analysis, it analyzes the way agents can move along network features. And network analysis can technically be done in both raster and vector, but vector is overwhelmingly more common. It's more common to use points, lines, and polygons. There's no way, ArcGIS doesn't have a tool for accepting raster data in. So when I gave you the example of the coral reefs, that I said I probably wasn't going to talk about, we actually had to take the raster data that was the ocean currents and then figure out the connection between all the different coral reefs. And then we just drew lines that represented those and assigned the attributes to those lines to build the network. So the lines themselves weren't the exact path that the coral reef larvae were going to follow, but it did say how long it took or the strength of the connection between different coral reef areas. And sometimes in a network data set, the lines don't represent the actual paths they follow. For example, if you had the network data set that represented all of the potential connections, let's say you were working for an airline company, so you had all of the potential connections for an airline company, you could model all of that in a network data set, but it's likely that your lines would just be straight lines between all the connected cities. It doesn't mean that the airplane actually flew that exact path. The point is actually that, okay, here, maybe I'll say this a different way. Let's say we had a line, and that line represented a street. Well, if we want to build a network in ArcGIS, how to do that, we actually have to have a field. Even if we wanted to use the length as the cost, we have to tell it that's the cost. So in the end, it's an attribute. It's not, doesn't have anything to do with the physical property. And if we had a really long line and we made the cost, 0 to travel across it, then it would always get chosen. That's what I'm talking about there. So I actually wrote that. At present, network analyst is not fully implemented in ArcGIS Pro. You can analyze a network data set, which is really the cool part, but you can't create a network data set in ArcGIS Pro right now. All right. I already gave some examples there.
So,
Okay.
Dr. Ray,
Yeah.
are you saying that there are models, modules that you can add to ArcGIS with the model work without ArcGIS or like that?
So in ArcGIS Pro, you no longer have to activate the extension. It just kind of knows if it works or not.
Okay.
But this network analyst button right here would be either grayed out or it wouldn't work if you didn't have the proper license for network analyst. Does that make sense? Okay, so we can map all sorts of things. I talked about airlines. You can do shipping lanes, migration paths. You can even do social networks, things that aren't even spatial. You could model them. There's probably better tools, but you could model those things. Like a social network, like you could model how connected people are. Like maybe you could get on their social networking platform and you could mine that data. You could determine how often person A comments or reads person B's stuff. And then you could build a network, and the cost or the impedance factor would be inversely related to how many times they had made a connection or talked to each other on the site or posted, however you wanted to measure it. But you would have a very low number if they frequently talked to each other, right? Then you could actually put that information in GIS. I don't know why you do that. You put it in there, and the lines that you made would all be that inverse proportion to how close their connection would be. Then you could then use Network Analyst to say, let's say I wanted to tell somebody something, and I wanted everybody to find out as quick as possible. Who should I tell first? That's the type of question you could answer with Network Analyst. Okay, and that's it's technically a location allocation problem, but I'm applying this to a different network, and that's why it doesn't seem like it should work. But in reality, it's the same exact question as if you said, hey, I want to build a warehouse and I want to put it in the location that will be able to have the least cost to travel to all my other locations. Okay. That's the same exact, well, it's not the same exact question, but it's the same type of question, just in two different networks. Okay, so there's way more application to this than just roads. So there was a guy about a year ago. He was a biologist. I forgot who his advisor was, but he was back there in the back of the class working on the computer, and I said, hey, how's it going? Anyway, he was trying to figure out how to use Network Analyst on a stream network to model some fish connections, like, which areas of this stream were more connected to the other areas. And so biology, all sorts of things. Transportation networks. So here's an example using freeways. That's just an example. I think we've already talked about that enough. Yeah, go ahead.
One you could use for like airlines and the routes that they use for like connections, or when people are like booking their flights to see which connection is going to have the least layover time, or which connection is going to have a little bit more of efficiency getting to wherever you're going.
Yeah, yeah. I mean, you could build like I said, you could build a network of all airline routes, or optionally, you could actually build. You could use it to answer a question. Like, so if you had a bunch of hubs, potential hubs, like let's say I was FedEx and I was trying to decide where am I going to put my hub to disperse my packages every night. I could have a hub and then a bunch of potential airline flights and their lengths and their times, how long it took to fly to all these places, and then I could use the Network Analyst to determine which hub would be best to get to all those locations. So I have the places I need to go, and I have the hub locations, and that's also the same location allocation problem. So those should be answered by that. All right, so we kind of talked about this a lot already, but we talked about edges and junctions, and then edge-to-edge connections. So edges can be connected through junctions, but they don't have to be. So there doesn't have to be a node. There can be an edge-to-edge connection. In other words, one edge touching another edge directly. Okay. Those are just some examples of where that could happen. But really, stoplights could be modeled as junctions so that they would have extra costs associated with just the points. So the real key here is that you have your weight, which is an attribute. It's the cost, and it can be assigned to edges. It could be assigned to junctions. Typically, this would be the travel time. This would be the stop time at a junction. There are other features that you can put in, okay? But these are really the only necessary features: the edge and the junction. You can feed it things like barriers. You could say, okay, here's a barrier, and that means that travel cannot go through here right now. Okay. Optionally, you could just assign, like I said before, you could just assign the edge or the junction a infinitely high value, and it would no longer choose that path as the best path. Okay. That's really what the barrier is doing physically inside there, but barrier is another feature. So usually we have edges, junctions, and barriers. So barriers are helpful, like if you're trying to model, if you were saying, okay, I got to leave because the hurricane's coming. What's the best path out of here? Well, we can model any road closures or lane change directions, or even maybe some preliminary flooding. Put a big polygon and say this is a barrier. Can't travel through here. And so then it would choose a better way or a different way to get out.
So as you were saying that as we're hurricane here, the traffic reverses going up north to the south. So it's normal that but based on the type of emergency or the thing, then what was been a barrier before is not a barrier. So those can change based on the change based on the situation, right?
Right. Yeah. Yeah. All these things change based on the situation. Yep. And we'll see. We could do, even with the tools as they are on the desktop. There's not necessarily live or real time. We can do some different scenarios. We can throw in some barriers to do that. So in general terms, like in mathematic terms, because really this is based on a mathematic concept of a graph. Okay, but ArcGIS and depending on the software package might call these things different things. Like they might call them sources and destinations. But once your network's built, you're going to have to run it, to use it. And so these are additional features, but these features aren't part of your network usually. These are features that you're feeding it to answer a question. And so you feed it usually two sets of data. Where the agents are originating from, those are the sources, and where they are going to finish what they're doing, those are the sinks. Okay. So all sorts of networks have those, but the example is the commuters going from this place A to place B. So in my, do I still have Google Maps up? Yeah. In my example, okay, I just had one source and one destination, or one source and one sink. The agent was going to go from here to there. But they could be, like in my other example, with the coral reef, they would be the spawning areas, and the sinks would be the settling areas. This says the ocean. It should actually probably be the areas that they settled. All right. So once we have our network set up, and usually we have identified what our sources and destinations are going to be for our particular problem, we're ready to run. And these are the problems that can be answered by network analysis or doing network analysis. Okay, the one that we've seen already is the shortest path. So in other words, I want to know how to get from point A to point B along a network. That's probably the one that gets run the most. I don't think there's really any other one that's cooked into a web app that's free like that. So that's the shortest path. And we're going to talk about each of these. So we're going to we're talking about these. Some look to, well, this actually should be indented in here. The shortest path tries to minimize the total distance traveled or the total time. Okay. But there's other things that we could do. We could actually put real cost in so to maximize profit and things like that. All right, this is the slide that I thought I was on here. So these are the different types of operations we can do. The best route, the closest facility, and then we've got allocation, which includes location allocation problems. And then the location allocation problem is really doing this origin destination cost matrix in the background, and I'll demonstrate that. And then finally, network partitioning. So we'll talk about each of those. So first of all, let's talk about shortest paths. So even Google Maps has this capability, but shortest paths will allow you to specify what your origin and your destinations will be. You can actually specify multiple destinations, and you could specify that you want to stop at each destination for a little while. All these capabilities are built into ArcGIS and other software packages. And what's actually happening here is that the shortest path analysis finds the path with the minimum cumulative impedance between nodes in a network. Okay. So the path may be connected between just 2 nodes, or it may have specific stops between the nodes. So more likely it's going to take more than just 2 nodes to complete it. Okay. So it builds a shortest path in between all of the networks. And really, once you build the network, what's actually in the computer's brain is this table of all the connections, rather than where this line actually goes. You know, if it was a windy road, it doesn't really matter to it. It's just what the impedance value is. All right, so best route is really the same thing underneath. It's the quickest, shortest. We could also do the most scenic. So you could actually imply an impedance value that was weighted so that it provided a lower cost to roads that were more scenic than roads that weren't more scenic. And you could play around with how much scenicness offset the travel time. So you could actually maybe have a slider in your in your application where, you know, if you really wanted to weight it towards scenic, then it wouldn't care how far you went. It would still try to hit all the scenic routes. And then you slide that down, and it could just be a simple thing where it multiplied the scenic value times the travel time, and that multiplier was, you know, times like it weighted one by half and another by half, or it weighted one all the way or one all the way. And you could see how it would change the network. Change the answer to the best path over time. That would be an application of doing it that way. So I'll start doing some demos right now. You don't have to actually download this data. I don't really have much data downloaded at all. But what I'm going to do is start off, and you can do this. What I'm going to do is start off with, if I open up ArcGIS Pro, and you all have this capability. If you choose, this is under analysis, by the way. If you go under analysis and you say choose network data source, if you choose arcgis.com, it actually chooses this default worldwide network data set that's built everywhere. And you can't see it, but it's the road network for the world. Okay. So I have it. I've chosen that as my network data set. See that? And And now I can do things like I can do any of these problems. So I've got the route. That's this this one that's the shortest path or the best route. They're really almost the same. One's just saying the point between point A and point B. The other one's saying what's the best way to go from point A to point B to point C to point D. Okay. All right. So once I load up that route, see how I load that up, and it's going to put that in my table of contents. And what that's doing is it's telling me you want to do some analysis on that network data set that you can't see, but it does exist. And here are the features that you're going to feed it. These are the stops are the locations that you want to visit. Yeah, do you have a question?
Yeah, it's a little hard to see on the network analysis. Which one did you put?
I clicked route.
Wow. I got it. Thank you, sir.
Okay, no problem. So
Any other data?
what's that?
This example? Like
No, it's actually using a network data set that's in the cloud. In other words, ESRI built this network data set, and it's going to use that network data set. So I don't need any data. As long as I set this to www.rgis.com, which is the default. So you might not even have to set that. All right, so now to get my stops in, I go to the route, and there's this button called Import Stops. Okay, if I click that, it's going to ask me for my locations. See, I have to actually like provide it locations. I think I can, well, that's barriers. I was going to show, I think, I wish you could just like put points down. But I didn't picture you all following along, but if you want to, I did upload this data. So let's just say I have all of these points, right? I just put these points up on the internet. You can download that data if you want to. If you want to just follow along with what I'm going to do on here, you can. Okay. So let's say I want to get from one of these points to another point. Well, I can simply highlight one. I can go to select. I can highlight this point. It's a little more clunky than Google Maps, right? I'd have to create a point. I don't know what point that represents, but I'm going to make this one of my stops. Actually, I'll just make like several of these stops. So I got 3 there, right? 1, 2, 3. And I'm going to import my locations from that data set, which is called Midwest Urban Points Training. And it's only going to select those, it's only going to import those 3 points. So I'm going to run that. And when I do, it imported into that layer. So now I turn that off and I turn this on. See that? So I have those 3 points. And those become my points. I go back to route. And now I can solve this problem. Now, if I hit solve, then it'll start working here. But notice the options that I have to solve this. I can choose, because the network's set up this way, these are all the attributes. Driving distance, driving time, rural driving distance, rural driving time, trucking distance. These are all the different modes of transportation, and they're just going to draw from different attributes of the edges and the lines. The sequence, I can actually specify, hey, I want you to go from 1 to 2 to 3. That's use current. Used best, find best means that I want you to arrange them in order. Now, programmatically, all it's doing is trying out all three and reporting out the difference. That's what it's going to do no matter how many you have. It's going to try to optimize those, like it's going to try a few and then figure out, well, these aren't going to work at all. Okay? But really, in the end, it's got to try out a number of them to figure it out which one's the best. Okay? So if I say use current, for example, I'm just going to hit run. It's going to go from 1 to 2 to 3, showing me the best route from 1 to 2 to 3. This is doing the same thing as Google Maps was doing, except for I've chosen different locations. So it's telling me I'm going to go from here to there to there. That's the best way to go to those 3 places. Now, if I wanted to say, I don't care where you start and where you stop, I'm going to go find best. In real life, why would it sometimes matter where you start and where you stop?
That's where you are.
Yeah, like if you were at a particular location, you would want to know. However, if you're trying to plan for locating a traveling salesman, then it doesn't really matter where they start and where they stop. You just need to know which one's the best. So you could say, okay, well, you're going to live here. You're going to go over there. Yeah. So finding the best means I start here in this Missouri one, go to this northern Tennessee one, and finally end up in northern Indiana. So I could say preserve first and last, but all the other ones can change. I could say preserve only the first stop or only the last stop because the person has to live in a certain place. So those are all different options in the analysis. If I open up the routes at the end here, it'll tell me how long it's going to take. So just like Google, it'll report that. If I open up the attribute table, so this route here is everything's null except for the one I chose, which was just the, did I say distance? Oh, total travel time. So total travel time is what I did. So that's 739 minutes that it's going to take me to go from here to there to there.
Can you just real fast show the geoprocessing screen of like how you plug this in? Because I ended up downloading the points. I just kind of want to see.
Which geoprocessing screen?
The add locations.
Okay, so import stops is right here. I hit this.
Yeah, I have that.
Oh, okay. Then I just hit the Midwest training, but I made sure I only selected 3 of them because it's going to take forever to solve the problem with all of those points. Not forever, but it's going to take a long time. So, like if you put in, 100 points or whatever, you could do it, but it would be a little while. Right. Now, I also, this was part of the lab that you're going to do. I also downloaded a data set this isn't included in Canvas, but it is included in the data set that you would download for the lab. It's called ESRI training. I'm just going to get one of these. So San Francisco transportation. So I load that guy up. And this is a network data set that's in San Francisco. There we go. I'm going to zoom to it. So there it is right there. So it's a network data set. ESR, this is also an ESRI data set. So my guess is they just kind of subsetted out that data set. So now if I want to make sure I'm using that, then that's right there. So I am using that now. But I can change the network data set back to arcgis.com. But you can use a local network data set is the point I'm trying to get across here. All right. I'm going to go ahead and turn this guy off for a while. Zoom back out. So that's the best route. Closest facilities requires sources and sinks, not just places you want to visit. So all the rest of these actually require sources and sinks, or sources and destinations. So now if we say, hey, we're going to do network analysis, and we're going to choose the closest facility. Let's turn this route 1 off. Okay. So again, this one exists everywhere in the United States. So we have ArcGIS is calling them facilities and incidents. So facilities are the locations that the agents are starting from, and they need to serve or go to the incidents. So one model might be like these could just be like police stations and crime, right? So in this model, the facilities aren't like we're not choosing a new facility. We're just saying these are the facilities. Which facility should serve these incidents? So we could go back to my training data. So we got all these points, and we could select, this one, that one, and we could then do import facilities and choose that data. See how now those will become facilities? And then we could actually, I'm actually going to just take all of them and make them, just in the interest of time here, I'll make all of these incidences. So we've got all the rest of those places are going to be incidences, and run that. Okay, so we might want to ask, what is the closest facility to each of these incidences? Then we just hit run here. Obviously, we can change from driving time to walking time or whatever. So
the sources or the sinks are the facilities. I think it would be the sink would be the facility, right? Like the destination.
No, in this case, the facilities are the origins. They're where it starts. Like they're serving the incidences. So it's kind of like they're going out from the incidences.
So it would be like grocery stores and houses. Like the grocery stores would be the facilities, and then the houses would be these sinks, because that's where they're coming from.
Yeah, I mean, in that case, people are traveling to and from, so you could model it doing that as well. But this is looking at the path from the facility out.
So wouldn't the 6 be the termination of the source? The end point of the source?
The end point of the trip is the
trip. So the
yeah.
source is where you come from.
Right.
When you're,
So these are the routes. I'm pretty sure we could open up the attribute table here and look at all these routes. So here's an individual. There's one of the routes from that facility to that destination, and from that one to that one. So we could see the facility ID. So we could, which I think would make sense, you could do something like this. I'm going to clear, and then hit routes, double click right there, and do the symbol as a unique value being the facility ID. facility ID. I want to add all the values. It's just saying all other values. I know that they're not all the same. I don't know why it's forcing me to add those individually. Usually does that by default. Trying to get the line width bigger. Not that big. Ah, there we go. Okay. And then I don't like this yellow color. So we'll make that orange, I guess. Okay, so now by symbolizing it, I'm just doing it cartographically. I can say, okay, well, these are all the facilities that are going to be served. I'm sorry, all the incidents are going to be served by that location. These guys are going to be served by that guy. These guys are going to be served by that guy. Let's go. So another application for this might be I have a bunch of emergency response stations set up, like FEMA stations afterward. And so as incidents come in, I can load them in here, press a button, and figure out, which incidents of flooding, which one you're going to go to, and I can report back to that.
That could also be the which stores is stocked by a warehouse and kind of thing. Like
Yeah,
which warehouse
exactly. Which warehouse is going to serve which grocery store? Yep. Exactly. I'm not gonna do all of these. Okay. So closest facility goes out and it's based on actual incidences. Well, service areas is kind of similar in that it assigns areas to their closest facility. So it's called service areas. So service areas doesn't require any destinations, incidences, other ways to say that. So if I go back to analysis, it's kind of like doing a buffer. It's like saying, how far can I get in 1 hour, in 2 hours? So really, service areas and closest facility are very related in that in the background, it could just be doing a service area and then doing a spatial join, right? But it still would need to find the exact route. But if I take my service areas and I import facilities, I'm just going to import them all because that would be the easiest. So those are all my facilities. And let's say I want to find out the driving time, 5, 10, 15 miles away from the facilities. I do have the opportunity to say towards the facilities, either way. So this might be useful in planning, figuring out, like I could use this as the first step. I could say, hey, I've got my networks, and I want to find out how many people live within 15 minutes of all my grocery stores. Well, the first step would be to run this, and it's going to find out, this one's going to do multiple buffers, 5 minutes, 10 minutes, 15 minutes away of those facilities. That might take a little while. So maybe I should have just done 3. And then the final one is location allocation. Oh, I finished. Cool. Talk about location allocation in a minute then. It doesn't look like anything, right? Well, at this scale, you can't really get very far. So I'll zoom in down to one of these. Okay, and you see there's three polygons. There's this polygon right here. Then there's this polygon, and there's this polygon. And those polygons represent how long it takes to get from the center of this town. That's what this is, the center of town. Let's say this represented a grocery store. How long it takes to get 5 minutes away? How far you can get in 5 minutes, 10 minutes, and 15 minutes. So why do you think there's this little like spider coming out of this area right here? And you see there's another longer one right there.
Probably like a freeway or an interstate, so they could probably go further distance quick.
Exactly. And then notice how you can't get out here at all, right? Even though that's pretty close. It's probably because there's not even any roads there.
Even on the south side, yeah, that's a big old area. It's not
Yeah.
like really far.
Yeah, you can't even get here at all, probably because there's no road. And then some of these, there is probably a road. There's probably a bridge somewhere. You'd imagine.
Is that water? It's
This-
hard to see it on ours.
This is
Yeah.
a river.
Oh, okay.
Yeah, well, that's probably watersheds.
Yeah.
Can you color code those zones, or are they just different shades of yellow?
They're different shades.
They're different shades of yellow. You could change them if you want. Look at how much different. Like getting out of Springfield takes a lot longer than getting out of Champaign, probably because it's a smaller town. What's that?
You're almost into the next town by that point.
Yeah. And these are just like arbitrary. Like I didn't put in Chicago. I mean, I just pulled them out so there wouldn't be a whole bunch of them.
Hey, Dr. Ray, is that how Walmart do it?
I'm sorry.
That's how Walmart do it, the neighborhood stores?
Yeah. Yeah, Walmart, I'm sure Walmart uses similar software. I'm not sure if they have a ESRI contract, but there's other softwares that do similar things. But all right, so location allocation is the last one we're going to talk about, and you've heard me mention it before, but basically it measures the efficiency of facilities or schools in terms of the service areas. It's useful for planning potential locations. So it helps you choose which facilities from a set of facilities operate based on their potential interaction with demand points. What it's really doing is it's measuring the centrality. We'll talk about centrality in a second, but it's measuring the centrality of your specific facility points in a network. Okay. So we'll go ahead and, since we've done them all anyway. So let's say I have, these are all, I got to create one. So,
Can population size be a source point, so that you can model based on that source point? Population size, like we might have 10,000 individuals, that then use them like model, getting stuff in the facility as opposed to those population groups.
what's the question that you're trying to answer?
The question is, can a group of people be a particular source that you want to model to, because you want to know if you need to put up facility environment. You look at it in those terms, population groups, like those dots in population group instead of stores. Can you model something, because you want to get a facility close to,
Many people as possible.
yeah, many people possible that way sometimes build a store. They don't know that.
Yeah, I mean, you're going to have to define the problem a little bit better, but people can be included. Like in the example I just said, what if I wanted to find out how many people are within 15-minute drive time? Well, I have to have a layer that represents people, and then do the drive times, and then do the overlay to figure out how many people there are. It's a two-step process. If I want to go, the reason why I'm struggling with your question is you're saying, can my origins be weighted by how many people live there? Well, my question is, why would you do that? Like, I need to know, I need to understand.
Why do I want to build a place by small amount? I'm going to put $1 million store and only 10 people in that area. I want to find the largest group and find in between those two or whatever. The ideal location to put the store, because they only going to drive 10 minutes a day, really don't want to do it. So.
Yeah. Well, that sounds a lot like my example. I have a layer representing population. I have my potential store locations, and then I run drive times, 15 minutes, and I figure out how many people are within 15 minutes of each.
Right.
Okay, so with location allocation, what I would do is say, okay, here is my demand points are all going to be all of these points. So I'm going to feed them in. My demand points are going to be like my demand points are going to be the current store locations, right? Like, let's say I'm trying to cite a new distribution facility. So my demand points are my current store locations, and I could put those in. Input locations are going to be my small set of points. I run that, and these are now all my demand points. Just to make this easy, let's see. I'm going to say one of these is going to become the potential distribution facility. I could have another set of data that represented the distribution facility areas, but I'm just going to say it's going to be the same data set. So I'm going to feed the same data set in as the facilities and the demand points. So those are all the demand points, and then those are all the facilities. So then I could run this, and by default, I'm going away from the facilities to the demand points. I could choose the opposite. I could also choose the type, and I can also actually choose that I want more than one facility. Right now, I just have set for one facility. So right now, it's going through here, and what it's actually doing is calculating the costs associated with traveling to and from every single point that's a demand. They're the same points. So there's going to be some that are 0. But every single demand point and every single potential facility. That's what it's doing right now. And then the next thing that it's doing is all it's doing is finding out. So for point 1, there may be, well, I don't know how many other points there are. Let's say there's 40 other points. There's 40 other points, and so it's getting the total of all of those other points. The travel time to all those other points. So that's the best one. I mean, we knew it would be in the center, right? But that's the best one. But we didn't know if it would be that one or that one, right? Or this one or that one. That's the one that it chose. So in other words, that point has the minimized travel time to all of the other points. That's one measure of centrality. One measure of centrality is that it has the shortest travel time to all the others. So going back to that social network example, if this was a social network, they have the strongest tie or the least cost to all the other people in the network. All right.
That's the concept of centrality, you said?
Yeah. Yep. And I have a few slides on it here in a second.
Who did competitive information come from? You said competitive. Is that something you said in there, or is this just a program?
I didn't hear what you said, Elvis. Sorry.
Competitive. If you look at the facilities, it says competitive. Is that what you might use to model the closest one?
Oh, competitor, right here. Yeah. So you can do different types of analysis with this. So competitor would be if I imported facilities, I could say, hey, I want to import competitors. I'm not exactly sure how it works.
You probably could do it with Dollar
You know,
General,
probably
$50.
Dollar General and just Walmart, and you might want to see how close.
Yeah. Yeah, it'd be something to check out. I've never used that one.
I bet that's what it's used for. Gotta be.
Yeah, it's gotta be. So you go into the help and you can read all about. Oh, that's add locations, not location, allocation. Oh, that's on the page. I would search for location, allocation, ArcGIS, and then read about what that particular one does. Competitive. Yeah. It must be new because it's not. This is actually Arc Maps help, so I go to Arc Pro and check in there. But I don't see competitor in there. When you well, it's not a matter of slowing down. I don't know the answer, and so I'd be investigating the answer.
It looks like you've been creeping up with the program.
It'd be better for me to investigate the answer offline. What's that?
But it's probably symbolic. It's some symbology with businesses too, I guess.
All right. Okay, so that's location allocation. Now, when I said what it's really doing or what it's doing in the background is actually finding out all the connections between every point, there's a tool for that. That's called the origin destination cost matrix. The origin destination cost matrix will actually give you the travel time between every single pair of points that you want. So it's basically the raw data that gets used to create the origin destination or the location allocation data set. So if I did a origin destination, the result is going to be a table. It is actually going to show you the lines, but the lines are just the connections. So if I do the same thing where I import all of those same points as both the origin and the destinations. Training, run those. And then run this guy. So now it's going to figure out the travel time between every single pair of points. And I'm going to have that table. And then I'm going to show you how, using that table, you can get the answer that's at location allocation. So you could use this for any type of problem. In fact, if you wanted to figure out, like, let's just say, in practicality, you have these 2 points, and they're really, really similar. Remember, this one ended up, sorry, I should do this over here. This one ended up being the one with the best location allocation value. But if you were wondering, how much worse would it be if I just went here, because there's some other mitigating circumstance that makes that site slightly better, you could wonder, how much difference is it between these 2 sites? You'll have that information in the location allocation data set. So that ran. See, now the output is this big jumbled mess. But every single one of those lines has a cost associated with it, and it represents the distance to travel over that path. So I'm going to open up this attribute table here and see if I highlight one of these. No, not line barriers, lines. Sorry. If I highlight one of these, then it's going to show me one of those lines. I don't see where it is. It's probably really small. Maybe I could zoom to it
Flash it.
or flash it. Let's choose a different one. There it is. So that's number 2. That's number 3. So you can see that's the connection between this city and that city. Okay. All right. So
Can you sort them and find out what's the best one based on sort channel, sort one of those fields?
well, but what do you mean by best? This is
The reason why I'm trying to sort because the center one is their field for the center value, to find the best one based on the center value, or they based on
yeah. So let's think about that question because it's not just a matter of. So if we just sort by travel time, we're just going to get the 2 points that are closest together on the network. Not closest together. They have the shortest travel time. So travel time between these 2 towns is the shortest travel time on the network, which is 15 minutes. It takes 15 minutes on the network to go from this one to this one. Not along that path, but along the path. Okay? The question that we really want, though, to make this the same as the location allocation, is we want to find the sum of all the travel times from every origin to all the destinations that are from that origin and that same origin. So, like, from this one to all of the other ones, what's the total sum? From that one to all of the others, what's the total sum? Okay? So, if you think about that for a second, what GIS operation is that? Where we want to, what do we want to do? Well, we want to summarize total travel time, and we want to summarize every one what? We want to summarize all the origin IDs. So for every origin ID, we want to sum all of the total travel times associated with every origin ID. Or if we wanted to model in reverse, like in other words, how long would it take to flow in, then we would summarize all the destinations. Okay? But we want to summarize all the origins. So we take all the origins and we want to add up. Here, I'll sort it by this so that it makes a little bit more sense here. If we sort this, see how there's these ones, these 2s. We want to add all those 2s together. I think there's more of them. Oh, there's way more than one. Okay, so yeah, here. Let's go all the way down to the last 2, because there's one for every connection.
Maybe select by attribute and calculate field.
Zoom out here. Yeah, so there is all of the connections to point number 2. So that must be point 2. And what we want to do is add up everything in this column that's highlighted. You propose we can select out number 2 and then add up the total travel time, right? That would work, okay? We could do that. We'd have to do that for every single point. And if there were lots of points, it would be lots of problems. But maybe we could write a script that would do it, and it would be great. Okay, but there's a tool that will allow us to do it in just one tool, and we've used it before. So think about this. Really, we want to take all of these lines, even though those lines don't represent real things, we want them all to be one feature, and we want to know the total value of that one feature. Dissolved. Yep, you got it. All right, so I'm going to clear it, and I'm going to dissolve. So I dissolve the cost OD cost matrix 4, which is called right here under lines, and then the dissolve field. What should this be? This is the feature that all of these will become one feature.
Origin ID.
Origin ID. Good. And then we want to sum up which field? Total travel time. And we want sums the default. So now when we run this, it's just going to save it there. I don't care where it saves it for right now. When we run this, there it is, lines dissolved. We look at the attribute table. Now we only have, if we highlight one of these, it's all of the connections from that point. And now, like what you said, Elvis, we can sort this by ascending, and it's the same one, 31. So it did the same thing. We kind of just like proved that it worked. So that point right there, let's zoom in and make sure it's the same point, because it could be the other point, right? But we'll zoom in. It's for sure that northerly one, not the one right below it. But if we did want to ask, what's the difference in total travel time between this one and this one, we could do that, okay? Because we have to find out what ID it is. But my guess is it's going to be one of those other ones. So open the attribute table. That's the one we selected. Let's see what the second most one is. It's the second least travel time. And the difference in minutes is about roughly 400 minutes in total travel time between those two. Okay? So we can decide, hey, is 400 minutes travel time worth it? Is it, if there's some other factor that's causing that to be a little bit more desirable, then we have a concrete number in which to report and say, hey, it's going to take us 400 more minutes of driving each week to do that one versus this one, which is how many hours.
It's possible one of those facilities can burn down, and then somebody may ask you, what's the next best place?
Yeah.
You got them all in order.
So you got them all in order, exactly. All right. All right. So that's the origin destination metrics, and this. Oh, yeah. Sorry.
Before we move on, you mentioned when we first started going over the origin destination, like how it was related to the location allocation, like so they're used in one another. Is that what you were saying?
Well, yes. So the origin destination matrix is actually what's driving the location allocation. So it's basically ArcGIS is kind of like, they call it a different analysis, but it's doing the origin destination, it's doing that dissolve, and then it's choosing the top one and letting you know what the top one is for you. So does that make sense? That's why I went through that exercise.
Okay, you were just showing that you use the origin destination in the location allocation. Okay,
Right.
cool.
So the origin destination is kind of like the raw data that drives the location allocation. Does that make sense?
Yeah.
Yeah. So if you want the raw data, you run the origin destination cost matrix. If you want just the answer, just give me the answer, then you run location allocation. So
And just based on distance and time in this particular.
you could base it on either, whatever your network has. If your network has time and distance as two different attributes, you could run it on either one, right? So the last concept here before we take the break is that this is one method of calculating what's called centrality. And centrality is a concept, or it's a metric, kind of like figuring out it's a descriptive thing about a network. It's kind of like figuring out the average from a set of data. Centrality is what does it mean to be central? So centrality could be, is it important? Is it well connected? Is it close to everything? Centrality is a general term for calculating statistics that tell you these things. Which feature is the most important? Which one's the most connected? Which one's close to everything? Okay? Which one's in an area where everyone wants to be or to pass through? So the centrality of both nodes and edges can be measured. Okay. This concept's on, you could Google centrality and watch YouTube videos on it or something, but this is a short concept on it. So, and again, it's not really spatial. Like mathematicians work on this stuff, and it works in our GIS, but it doesn't have to be a spatial problem. All right, so here's a few different types of centrality that we're going to discuss. That we're going to try to figure out how we could do this in ArcGIS. So one is degree centrality. It's defined as the number of links incident upon a node or edge. Okay? That doesn't even seem like it would take network analysts to run. So sometimes it can be measured as a second level. That probably would take network analysis. So all the direct connections plus all the second level connections. You could even weight them by the strength of the connection or the impedance value. So when would you want to use this? Well, degree centrality gets used in this way. It can be interpreted in terms of the immediate risk of a node catching whatever's flowing through a network. So if a network has a bunch of cars flowing through it, and we're worried about people. It doesn't have to be a disease. It could be people spreading. It could be a rumor or the way people drive or the way people interact with each other. Anyway, or it could be a natural phenomenon where we're worried that this species is going to travel in a certain way. We could use degree centrality to measure how important a specific node or edge is. In other words, how many incident links does it have? It's a really basic measure of centrality. How many ways in is it? And we often call Hattiesburg the hub city, right? You hear that. Hattiesburg has a lot of different ways to get into it. So it would have a higher degree centrality than some city that only has one road in and one road out, right? That's putting it simply, right? The incident nodes, the ways in, tell us about the degree centrality. In transportation, in just like road networks, this isn't something that we calculate a whole lot. It doesn't have a lot of application, but it could have application, I think, more in the biological world. So we built a network for some fish species or other species and how it was communicating. It might be important to know how many ways in a particular habitat had. All right, closest centrality. This is the one that we just calculated. I think I was going to ask that in a second, but anyway, told you the answer. So closest centrality is the closeness of a node. It's defined as the average length, the shortest, the least cost path, between the feature and all other features on the graph, on the network. Graph is the mathematical term for a network. So the more central a node is, it defines it as the closer it is to all the other nodes. So this is the one we just calculated using the OD matrix, the origin, destination, cost matrix. And we could do that. You could also use location allocation to do that. So the application, where to put a distribution facility, but we could also use it in the social network to, again, figure out which person we would, if we had a social network and we're modeling it, we can figure out which person we should tell if we really wanted to influence a bunch of other people. Okay. Or in a biological environment, it might be, well, this is actually what we did in our study. If we were to make sure that we protect certain reefs that are spreading their coral reef larvae out, which one should we make sure that we protect? Because these particular reefs mix with way more because they're closer, they're more central in terms of their ocean mixing than the others. All right, and then finally, betweenness is another centrality measure. It quantifies the number of times a feature acts as a bridge along the shortest path between two other nodes. So to model this, it actually would require a script. You'd have to have all of the shortest paths modeled. And once you had all the shortest paths modeled, let's say you had all of your, let's say we did it with this. Let's say you had all of our facilities we have our shortest path model. How can we find out which facilities intersected with the most shortest paths? What tool could we use for that? In other words, another way to ask that same question that you might be familiar with if you've done Lab 3 is, let's say I had a bunch of cities. I wanted to know which cities touched the most tornadoes paths. Yeah, spatial join. So if we had, these aren't the real paths. So imagine that we had all of the shortest paths, like the shortest path from this city to this city, and from that city to that city, that city to that city. We had all of them, but we had the shortest path lines. Okay, and so we just want to know of all of these, which one has the most shortest path passed through it in a network. That is betweenness centrality. And it also gets used a lot in natural habitat applications. So if we had the some measure of how connected all of these areas were, then betweenness centrality would tell us which of these features is used as the shortest path between the different spotted owl habitats.
Is it almost like you're identifying choke points? Like if everybody goes on I-10, to get to, Florida, like if you wanted to shut down traffic into Florida, you just stop I-10, if all the paths were there.
Right, yeah. I mean, I guess you could call them choke points. So it's a measure of how important that edge or node is. How many times it serves as a shortest path between two other locations. Yep.
Okay, so you could probably use it in especially down here on the coast to find out which bridge is the most important to upkeep because it's getting the most traffic in because it's the shortest distance.
Right.
Like
yeah.
pop scares.
It would assume. I mean, in order to solve that problem, you'd have to find all of the origin destinations of people, or just sample that and say, okay, these are representative of most of the origin destinations. Okay, and then you could find out which bridge served as the most often connection between all of those origin destinations.
Okay.
Sorry, were you about to ask a question?
No, I was going to say it's more like the frequency of it. So
it is. It's the frequency of how often it's used as a shortest path. So this is the journal article where we looked at it. That's just the raw area. This is basically on the network. This is we actually calculated how much larvae was received from every island's jurisdiction, and how much larvae was contributed from every island to every other jurisdiction. So this is showing these became the strength of the connections. In other words, they were inversely proportional to the weight. So here, Cuba has a lot of coral reefs. They don't even allow most people to fish. Fishing is very restricted. You can imagine, because some people decide, hey, I'm on a boat already, and Miami's not that far away, so you can hardly fish there. And so they have really pretty intact marine environment there, and they actually showed up as having the most. Plus, they're pretty central, central as in they're in the middle of a lot of coral, because there's stuff on the west coast of the United States. They're a little out of the center, but anyway, yeah, they're contributing a lot to other coral reef environments, and they're receiving a lot of coral reef environments. So
What's B over there? C.
B is terms of raw, like volume, and B is in terms of percentage of the overall reef. Okay, so Belize is contributing a whole lot out into other reefs as a percentage of. So it's not a very big area, but it has a lot of reefs, and most of its reef is transported because Belize is kind of situated. Belize is it's in Central America, and it's close to Mexico to the north, and it's close to Guatemala and a few other countries that all have. There's a big reef right there. It's called the Mesoamerica Reef. It's the second biggest reef in the world reef system in the world after the Great Barrier Reef. And then C is the percentage of larvae that settled outside of the EEZ. In other words, almost all, over 60% of St. Kitts and Nevis larvae settled in other jurisdictions. That's the way you read that. But anyway, the way we used this was, this is actually a chart showing the to-from contributions between all the different countries. Yeah, so this is measuring for all the countries, for all the reefs, all the individual reefs. This measured their betweenness centrality here. So the bigger it is, the more central it was. In other words, the more often that reef served as an important bridge, just like with your bridges example, Ashley. So more often these reefs served as an important bridge, and so you see features like these are two in the Cayman's jurisdiction, Grand Cayman, and those are really important reefs in terms of there's not a whole lot of reefs around, and so they're serving as a bridge between the reefs on this side and the reefs on that side. They're really important. And then this is closeness centrality, and as you'd expect, this is more weighted toward the middle, toward the kind of like the density of coral reef, and that's showing how connected they are in terms of the least cost path to all the other ones. So as you'd expect, the ones on the outside have the lowest value, the fringe. So if you wanted to protect the core, you look at this. If you wanted to protect the ones that are important for maintaining those connections, you'd look at this. All right, so that's an application of a network data set outside of a traditional transportation network. And so these are just two, like if you wanted to just say 30% of the marine ecosystems. I think the top one here is using closeness centrality, or betweenness, and then closeness centrality. Maybe it's reversed, but anyway, those are the most important locations in the network. So you get Cuba and the Mesoamerica Reef show up in both. All right. So let's take a 15-minute break. I'm just going to go over what I want you to do in the lab, but it's pretty straightforward because you're just going to do kind of similar things to what I was doing, except for you're going to use some local data. You're more than welcome to experiment with the data that's on arcgis.com, but there's data to download in the lab and walk you through step by step on doing network analysis. By the way, you're not going to create your own network data sets. Someday we'll include that as part of the lab when they get that included. But it's pretty straightforward. You build a bunch of lines and you assign them weights, and then you walk through a wizard to build the thing. If you want, there's help on there. If you just click creating a network data set using our catalog. I could put the link up there.
Does ArcMap's online data set, is that worldwide? Is that countrywide? Is that?
It's worldwide. Mm-hmm.
Okay, so I wonder how accurate it is for Mississippi as far as Would it include like the smaller roads or just the main road?
It includes all the little. I mean, it's a pretty detailed data set. It's comparable to the data set Google has. Like you can click in individual points. It's not updated in real time like Google's, but it's.
Is there a way like you can actually see it? Like you know how
Yeah.
when you go into your network analysis, it's all.
If you zoom down in there, you can see the actual path that it's following.
Okay.
You just can't do it on this, but if I did the best route, it outputs the exact path.
Okay. So, but there's no way to see it before you do any like best route or anything like that. Just like see the actual data.
Oh, I don't think so.
Oh.
Yeah. I mean, you could load the streets data set, which I think is actually pulling the same data. So if you, well, let me turn all these off, or maybe not. Anyway, yeah. So if you change the base map to streets, then it's I'm pretty sure it's using the same data. See this?
Oh, okay, so that street file set is what they're using.
Yeah.
Okay, so I can check out, see if it covers the areas that I need to if I wanted to use it in my thesis beforehand.
Right.
Okay.
Sounds good. All right, so I'm going to stop the recording and.